So the summary notes were the ones that I handed out Friday, but they were the ones that went along with the summary video yesterday. So this also has the practice that we're going to be going through. If we don't get to the practice today, we'll do the practice tomorrow. The practice is, what type of reaction. So we'll look at what kind of nucleophile do we have, what kind of solvent do we have, what kind of reaction would it be, how do you know if reactions occur or not, and kind of looking through all of those different steps. We are going to review things today before we even get into the Kahoot. So I went through the questions, looked at questions. There were some with nucleophiles, some with solvents, and so I kind of have a couple slides where we're going to kind of talk about each one. So the first question, a strong nucleophile is needed for an SN2 reaction. What are some examples of strong nucleophiles? So within the notes, there is a slide that has strong and weak nucleophiles. The biggest thing is that a strong nucleophile has a negative charge. So you could go through and list a lot of different things with negative charges. Some common ones that we will probably see, hydroxide. Right, you would see it as sodium hydroxide, but hydroxide is a strong nucleophile. Could be a halide. So halide is just a halogen as an anion. Maybe something like NH2 minus. Notice each one of these have a negative charge. So a strong nucleophile is an anion. Now, we might see it as NaOH or NaCl or NaNH2 because we need that cation to bring the anion into solution. But you could have a lot more strong nucleophiles than just these three. Strong nucleophiles are something with a negative charge. Strong nucleophile means that it will attack easily. So a strong nucleophile like OH minus, it has the strength to attack a carbon no matter the type of reaction, whether it's a single-step or a two-step mechanism. Then number two, what are examples of weak nucleophiles? I said weak nucleophiles typically mean that an SN1 reaction will occur. So remember an SN1 reaction, that one means that there's only one reactant in the rate-determining step, which actually means that SN1 reactions are two-step reactions. The reason that weak nucleophiles mean that an SN1 reaction will occur is because a weak nucleophile doesn't have the strength to attack a carbon and kick the leaving group out. So a weak nucleophile has to attack when a carbocation has already been formed. So examples of weak nucleophiles, the two that we see the most are going to be water and alcohol. So I'm going to put ROH. That R could be methyl or ethyl. So if I put in parentheses, it could be methanol, could be ethanol. But notice how both of these weak nucleophiles are neutral. Right? These are molecules. They're not ions. Weak nucleophiles also tend to be our protic solvents. So our protic solvents tend to be our weak nucleophiles. We'll talk about the difference between the two on one of the next slides. And then lastly, which type of reaction is dependent on the carbocation formation, and when will this never occur? So we just talked about it actually in the second one. All right, second question. Carbocation formation means that there are multiple steps that happen. Carbocation formation would be an SN1 reaction. So carbocation is formed during an SN1 reaction. If a carbocation is formed, what are the unstable carbocations? Right, primary. So it will never occur if there's a primary, or we could even have a methyl carbocation. So methyl carbocation would just be all hydrogens, right? It would be CH3+. Methyl and primary carbocations are unstable. So if you were to form a primary or a methyl carbocation, an SN1 reaction cannot occur. Right? Instead of giving a product, we would just say no reaction. So that's looking at the do now, kind of some of the background information for SN1 and SN2 reactions. What we are going to do, we're going to go through some stuff within the notes. So you do want the summary notes out if you don't have them out already. So just to kind of start, and this is all within the do now slides. So if you need to go back and look at any of this, this top table box thing is actually in your notes. This one with the strong and the weak nucleophiles. So as we talk about nucleophiles, we are going to have to make sure that we can distinguish between the strong and the weak. A strong nucleophile has to have a negative charge. Notice each one of these strong nucleophiles is an anion. Weak nucleophiles are just molecules, they're neutral. So water, alcohol, those are weak nucleophiles. So they will still attack a carbon, but they don't have the strength to attack a carbon and kick a leaving group out at the same time. And then when you're looking at strength of nucleophiles, one thing with the nucleophile, looking at the strength of the two, the conjugate base is always the stronger nucleophile. So I just wanted to put this up to show you that each one of these, so if you're comparing, right, hydroxide is a strong nucleophile, water is a weak nucleophile. You have this NH2 minus, that's the stronger nucleophile, carries that negative charge. Right? SH minus carries that negative charge. So all of these that carry the negative charge are the stronger nucleophiles. So when you're looking at what's above the arrow or what's below the arrow, we first look at the type of carbocation that would form. Then we look at the type of nucleophile. Then we look at the solvent. And we kind of go in that order, and we'll go through the practice together as we look at what type of carbocation would form, what type of nucleophile do we have, what type of solvent do we have. But the nucleophilicity, right, strong versus weak, if it carries a negative, it's an anion, it's a strong nucleophile. If it's neutral, it's going to be a weak nucleophile. And then I kind of put a few things all on this one slide just to kind of have this single summary slide. This recap slide, like even in my notes packet that I always will kind of go back and reference and look at, this is like the most important slide. Right? This is the one that you want to use. Basically what I did is I took these recap slides and I just put them onto one to be able to compare. And so for these recap slides, I know I had like make flashcards. There's really just the two types of reactions, but you do need to know the difference between the two. So SN2 reactions are called a concerted reaction. It means it happens all at once. And so what happens is the nucleophile attacks the carbon and kicks the leaving group out all at the same time, which is why for SN2 reactions, if it's happening all at once, you have to have a strong nucleophile. And so for it to happen all at once, for that nucleophile to attack and kick the leaving group out, the nucleophile has to be strong. And because it's attacking on the opposite side, our stereochemistry changes. Now, we're not going to go through and look at that R and that S designation every time, but a lot of times if, let's say, a methyl group is a wedge, then once we have this reaction happen, that methyl will turn to a dash. So we say it's an inversion of stereochemistry. SN2, because it happens all at once, we don't have to worry about carbocations being formed. And so since everything is happening all at once, the less steric hindrance, the better. So methyl and primary carbons are actually the best. It cannot work with tertiary carbons. Right? So if your alpha carbon is tertiary, there's going to be no reaction. So you look at what do you have when that leaving group leaves. Is it primary, is it secondary, is it tertiary? It will not happen with tertiary carbons because it's too hindered, right? There's too many groups around it, and so that nucleophile can't get in to attack. And then SN2 happens with the aprotic solvents. So if you have aprotic solvents, that's going to favor SN2 because aprotic doesn't affect the nucleophile's charge. Now the difference between protic and aprotic, we will talk about, it's down here. So we'll talk about the difference between the two. But the type of solvent, we kind of go in this order. So we look at the type of carbon that we have. Then we look at the nucleophile. Then we look at the solvent. Because sometimes you might see opposite solvents. You always look at the carbon first, then you look at the nucleophile, then we look at the solvent. So SN2 all at once. Right, happens all at the same time. Since it happens all at the same time, you need a strong nucleophile. SN1. So the 1 means that there's just one reactant in the rate determining step. Unlike SN2, that 2 means there are 2 reactants in the rate determining step. So that's why it happens all at once. SN1 happens in multiple steps. Since it happens in multiple steps, this is the carbocation forming mechanism. This is where, since carbocation is formed, we have to look at, is it tertiary, is it secondary, is it primary, or is it a methyl carbocation? Unlike SN2, in terms of the configurations, the stereochemistry, we have a racemic mixture. Means you're going to have 50% of one configuration and 50% of the other. So you might have 50% that the methyl is on a wedge, 50% that the methyl is on a dash. So you have both. You have 2 products, 2 major products. And because a carbocation forms, it works best with stable carbocations. So tertiary and secondary, it will work. Primary and methyl, we would say there's no reaction. Because those are unstable carbocations, they will not form. Since we're dealing with carbocations, something that's not in here that we still have to think about, and it might be worth making a note somewhere, like on this slide or somewhere in your notes. When carbocations are formed, you still need to keep in mind about hydride and methyl shifts. Right? So since you have carbocations forming, you could still have hydride shifts or methyl shifts to give you a more stable carbocation. And then with SN1, either type of nucleophile can actually work. So you could have a strong or a weak nucleophile here. If you have a weak nucleophile, it still is okay because the carbocation is formed first. So there's already that positive formal charge on the carbon. No matter the type of nucleophile, it can go in and it can attack that carbon. But then protic solvents tend to favor SN1 reactions. Protic solvents will stabilize that carbocation and make it easier. What they have actually found is experimental data that shows both types of solvents will work with SN1 reactions, but protic makes it go faster. So kind of getting back into kinetics a little bit. Obviously, we would want the solvent that makes the reaction go faster. Protic will favor SN1. Aprotic could still work, but protic will make it go faster. Now, the difference between the two. So I have protic and aprotic solvents on here. Protic solvents can hydrogen bond. All right, so protic for the proton is hydrogen. So a protic solvent can hydrogen bond. Notice that methanol, water, ethanol, acetic acid, they all have H covalently bonded to NO or F. So ammonia, NH3, would be a protic solvent. It can hydrogen bond. Aprotic solvents cannot hydrogen bond. You do not have hydrogen covalently bonded to NO or F. THF, DMSO, those are common aprotic solvents. Acetone. All right, so notice each of these, there's no H that could hydrogen bond. And so that's the difference between the two. The protic solvents stabilize the carbocation because you can have hydrogen bonding. Aprotic solvents cannot hydrogen bond. It does change the nucleophile. We don't get as much into how protic solvents change the nucleophile, but charge, electronegativity, type of solvent, all will potentially affect different nucleophiles. And then this was actually part of that intro activity. That was on the very last page, that summary page, that talked about, kind of where to go. Almost like a flow chart for how do you tell what type of reaction it is. So you look at where's your leaving group. Is it on a tertiary carbon, a secondary carbon, or a methyl or primary carbon? If it's on a tertiary carbon, the only thing that could occur is SN1. If it's on a methyl or a primary carbon, the only thing that could happen is SN2. So then you have to make sure you have the right conditions for those to happen. It's when it's at a secondary carbon that you could actually have either one, and that's where you look at the solvent. The type of reaction that occurs is based on the type of solvent that you would have. So that's kind of looking at the different types of reactions. We're going to go through this decision making for which way do we go, how do we tell what type of solvent it is. We'll look at the practice within the slides to kind of look at each one.